Algebraic number theory, the intricacies of exploring rings of integers and Dedekind domains. Exploring the depths of algebraic number theory, algebraic number theory delves into the properties of numbers through the framework of algebraic structures, focusing on their relationships and behaviors within systems like fields and rings. This field melds algebra, number theory, and geometry to explore the characteristics of integers, rational numbers, and their generalizations. Ring of integers. A cornerstone in algebraic number theory is the ring of integers within a number field. To grasp this, we first need to understand what a number field is. A number field is an extension of the field of rational numbers, Q, that is finite dimensional when viewed as a vector space over Q. Essentially, it is a larger field that contains Q. Within any given number field, the ring of integers, denoted as O_K, comprises all the algebraic integers in that field. An algebraic integer is a number that is a root of a monic polynomial with integer coefficients. This set forms a ring, meaning it is closed under addition, subtraction, and multiplication, and naturally includes the ordinary integers. For example, in the simplest number field Q, the ring of integers is Z, the set of all regular integers. In more complex number fields, such as quadratic fields like QS, QRT, or Ds, where D is a square-free integer, the ring of integers can encompass more than the usual integers. For instance, in QS squirt, -1, the ring of integers is Z squirt, -1s, including numbers of the form A plus B squirt, -1, where A and B are integers. These rings of integers in various number fields display intriguing properties and structures. One critical aspect studied is their divisibility and factorization behaviors. While the ring of integers Z enjoys unique factorization, every integer can be uniquely factored into primes. This property does not always extend to more general rings of integers. Algebraic number theory investigates these factorization properties, striving to generalize and comprehend them better. Dedekind domain. The quest for unique factorization in rings of integers brings us to the concept of a Dedekind domain, an essential class of rings in algebraic number theory. Named after the German mathematician Richard Dedekind, these rings broaden the notion of unique factorization. A Dedekind domain is an integral domain, a commutative ring with no zero divisors that satisfies several key properties. 1. Noetherian. Every ascending chain of ideals stabilizes, meaning there are no infinitely increasing sequences of ideals. 2. Integrally closed. Every element in its field of fractions that is a root of a monic polynomial with coefficients in the ring is already in the ring. 3. Every non-zero prime ideal is maximal. This means that the quotient of the ring by any non-zero prime ideal is a field. The ring of integers of a number field is a prime example of a Dedekind domain. Dedekind domains are crucial in algebraic number theory because they extend the beneficial properties of Z to more complex rings of integers, facilitating more sophisticated analysis. One of Dedekind's significant contributions was the introduction of ideal factorization to tackle the issue of non-unique factorization in some rings of integers. Instead of focusing on elements, Dedekind considered the factorization of ideals. In a Dedekind domain, every non-zero ideal can be uniquely factored into a product of prime ideals. This property reestablishes a form of unique factorization at the level of ideals, even when it might fail for individual elements. For example, in the ring Z S squared -5, the number 6 can be factored both as 2.3 and 1 plus less squared and -5, 1 squared -5. While this appears to breach unique factorization, considering ideals instead, we regain a unique factorization property. The ideals generated by 2, 3, 1 plus a less skirt, -5, and 1, skirt, -5, factor uniquely into prime ideals. Applications and further topics. Algebraic number theory has profound implications and applications across mathematics. It plays a crucial role in solving Diophantine equations, which seek integer solutions to polynomial equations. This field also significantly impacts cryptography, particularly in the creation of encryption algorithms that depend on the difficulty of specific number-theoretic problems. Moreover, Algebraic number theory intersects with algebraic geometry through the study of schemes and arithmetic geometry. It also connects with analytic number theory, where analytical tools are employed to solve problems about the distribution of primes and other number-theoretic functions. One of the crowning achievements of algebraic number theory is the proof of Fermat's last theorem by Andrew Wiles. This theorem, which asserts that there are no three positive integers a, b, and c that satisfy a circumflex n plus b circumflex n equals sine c circumflex n for any integer n greater than 2, was proven using advanced tools from both algebraic geometry and number theory, particularly involving elliptic curves and modular forms. In summary, algebraic number theory is a rich and profound field of mathematics that explores the properties of numbers through the lens of algebraic structures like rings and fields. The study of rings of integers and Dedekind domains provides critical insights into the factorization properties of numbers, allowing mathematicians to generalize and understand these properties in broader contexts. This field continues to be a vital area of research with extensive applications in both pure and applied mathematics.